Okay, welcome back. This is now 6.2. We're looking at uh, differential equations. In particular, we want the applications now, the growth and decay applications that you see in your physics class, maybe your chemistry class, and biology as well sometimes. First, we need a little bit more information on how to solve differential equations algebraically. Okay, so we had some nice approximating ways last time, and I said in general when you do these things, what you're really just doing is an integral. Right? It's an antiderivative type situation. But let's look at what's on the horizon. So in general, when you're presented with a guy like this, what we want to do is separate variables, so to speak. So this is not technically correct, but think of it as multiplying both sides by dx. Okay, so on one side you have dy, and then on the other side you have x plus 3 times dx. And then what we're going to do is sort of integrate both sides. And on this side you'll have y plus a constant, but we'll move the constant to the other side eventually. On this side we'll have x squared over 2 plus 3x, and then plus your integration constant. Okay. So that's my very quick introduction. Let's look at one more, number 7. Y prime is the square root of x times y. One thing to note here is you can have kind of trivial solutions, like y equaling 0 would work here. Note, if y was equal to 0, its derivative would be 0 as well. And then you could plug that into here, starting on the left-hand side, y prime equals 0, which equals square root of x times 0, which equals the square root of x times y. Basically, it's a solution. So, it's, what can I say? I don't know. Maybe this wasn't the best explanation of it, but it works in here, right? If you put 0 over here, any x value you put in there, it's gonna, okay, so anyways, there's that. Let's get back to just solving these things. So how do I solve it? Get all the y's on one side, all the x's on the other. Okay, so here we have it rewritten with the other notation. Move the dx over, move the y here, so you get dy over y equals square root of x dx. Okay. Integrating both sides, then on here, ln absolute value of y over here, it's x to the 1/2, so x to the 3/2 times 2/3 plus c. Okay. And then I want an explicit solution, and I want y equals something, and it's possible by exponentiating both sides here. Over on the left-hand side, you'll have absolute value of y. On the right-hand side, I'm going to rewrite it a bit using my rules of exponents. So hang on. This will be e to the c times e to the 2/3 x to the 3/2. If you drop the absolute value symbol, it's equivalent to putting a plus minus on the other side. So you have plus minus e to the c, e to the 2/3 x to the 3/2. This thing then can be replaced by a general constant. So all it is some number, and as long as you know y and x, it's going to give you that particular number. So you just replace it with a general constant. And there's always a question, the number e's can never be raised to something to give you 0. But we do have this trivial solution here such that if I put in y equals 0, I get a true statement, right? So what can I say? It is what it is. It works. That's what I'm trying to say, I guess. But there it is. That's your very quick introduction, maybe somewhat painful introduction to that topic. We'll return to it in a bit, so don't worry. All right, so the growth and decay. There's going to be kind of a couple traditional differential equations that everybody loves to work with. The first one is the growth decay formulas, which result in the exponential growth decay functions that you get in your physics class. So what it says is that the change in population with respect to time is proportional to the population. Okay? And then we could solve this thing. So in particular, let's separate the variables, integrate both sides, exponentiate both sides, drop the absolute values. We'll say this can be replaced. Obviously, the trivial solution, y equals 0, is there. So we end up with y equals ce to the kt. All right? And that's the formula that you use in your physics and chemistry class. The c value will be your initial population. And then your k value is your growth rate. If k is greater than 0, you'll have growth. If k is less than 0, you got decay. All right, so the next part is basically just applications of this. Yay, we're able to finally derive the formula. Now we just want to apply it in sort of a pre-calculus setting. Here's number 31. They give you a bunch of information, and you got to solve for your unknowns. Okay, so they give you a chart. This is radon 226. And they tell you the half-life is 1599. We don't know the initial amount, apparently. And we're looking for the amount after 1,000 years. We don't know that. But we do know the amount after 10,000 years. So the amount after 10,000 years is 0.1 grams. Okay, so the formula we have now for growth is, what the heck was it? So y equals a, or rather c, we always use a in the other classes, y equals ce to the kt. Okay. And basically we have to trace down c and k. So first, you could use the half-life to get the constant, the growth constant. So after 1599 years, there's only 1/2 of the c value left. So you could say when t is equal to 1599, the amount left at the end of the day is c all over 2. Okay. You divide both sides by c then, you get 1/2 equals e to the 1599k. Then you could take logarithms on both sides. So the ln of 1/2 equals the ln of e to the 1599k. The ln and e are inverses, so those kind of cancel. You get ln of 1/2 equals 1599k. And then you could solve for the growth constant. K is ln of 1/2 divided by 1599. Okay, so now I'm going to try to get the initial amount. So I have y equals ce to the ln 1/2 all over 1599t. And it's telling me after 10,000 years I have 0.1 grams. So 0.1 equals ce to the ln of 1/2 all over 1599 times 10,000. And then you just divide both sides by this element and it gives you your c value, whatever that is. What did I get? About 7.63 grams. Okay. So my initial amount, 7.63. Now I can use this information to determine how much I got left over after 1,000 years. So y, in that case, will equal about 7.63 times e to the ln of 1/2 all over 1599 times 1,000. Okay, and if you put that in your calculator, you should get 4.95. Okay, the growth version of this problem, you'll see in economics, basically you want to know maybe how long it takes for your money to double. So you'll be given maybe an initial investment, let's say $750. We don't know the annual rate. That's what we're kind of looking for. We want our money to double in 7 3/4 years. And then we'll want to know how much we have after 10 years. Okay. Okay, it's the same game. You start with this formula, y equals ce to the kt, and you try to track down your unknown variables c and k. This time the c value is given as 750. You use the doubling time now, so the doubling time says that in 7 3/4 years, you'll have twice this amount. So you'll have 2 times $750 in 7 3/4 years, 28, 29, 33, 1/4. Oops, this is K. Once you have that, then you can solve for K and divide both sides by 750. 2 is e to the 31/4 K. Take the ln of both sides. Okay. And then you'll get you'll get 31/4 K equals ln 2. So K must be 4 ln 2 all over 31. And you get an approximation if you want. It's about 0.089. So 8.9% is what we're looking for our rate. Then you can figure out how much you have after 10 years. So y is 750 e to the 4 ln 2 over 31 times 10. And if you plug that in, you get $1,834 about and 37 cents. Okay. Okay. One last example then. This is the Newton's law of cooling problem. So basically, if you like usually see it with pizzas in the homework and stuff, you want to know basically a formula that tells you how cold your pizza is after an hour or something like that. And the starting place, the differential equation where you start in order to produce that formula, is that the rate of change of the temperature is proportional to the distance between the temperature at a particular time and the room temperature. Okay. And it's from this thing you can solve again for another formula, and it's an exponential. It looks like an exponential growth formula. So let's try it. We'll have dy all over y minus, let's just call it room temperature, I don't know, c sub 0. Okay. On this side we have k dt. So we want to integrate both sides. This guy is a natural log, right? So natural log absolute value y minus c sub 0. equals KT. Exponentiate both sides. We need a constant there too. So we get ln, we get absolute value y minus c sub 0 equals e to the c times e to the kt. Then our final answer, once we replace this with a constant, is y equals c e to the kt plus this room temperature, c sub 0. Okay. So it's interesting to take a look at, but it is almost exactly the same thing as just an exponential growth formula. Okay, let's leave it at that.